Hi, I'm Saulo Machado. I work at Accenture delivering value of emerging technologies today. So I'll present today a case where we applied quantum to solve a real business case for the oil and gas industry. But I'll run first from how we do quantum at Accenture. Then I'll go through a little bit of the context of the problem, showing some results, and finally the benchmarks. So, first of all, this is not although I'm presenting here alone, this is a work of a large team that are from the experts in industry, from the experts in the technology itself, until the sponsors that believed in this kind of technology that we're applying. So all of them should be represented here today. Just to let you know about our quantum team, the technical part of it is also distributed across the globe. So I'm based in Recife, northeast of Brazil. You can see an arrow going there, but our team is actually distributed around the world. And I'm saying this because not only we can bring different ways of thinking to what we are presenting, but also a specific way of interpreting the scenarios at each industry. So it's good to have this kind of diversity and brought to the table. So our Brazilian team has worked with quantum since 2018. We have already 2 patents on quantum, and we worked from building the ecosystem to building the talents and filling the talent gap we have in quantum in general. Of course, in research, finding new applications for the solution as well, and connecting this kind of technology to the industry with different offerings. But I'm not saying this only to present how we offer or the offerings of Accenture, but also to introduce how this problem came to be. So it all started with the collision of 2 worlds, the expertise in the emerging technology, in this case quantum, and business experts that knew or found out a possible application of quantum in a challenging problem in the industry. The problem itself was the exploration of offshore oil and gas reservoirs. It was identified by different clients, and our industry leaders brought this challenge for us to create a possible solution with quantum. We discovered it was possible a good solution to go through with quantum. Because each attempt to drill or to explore oil and gas offshore costs millions of dollars. And currently the existing solutions that are run every day, they run on linear approximations to make it possible of actually the calculations that are done. That's basically represented here. If I try to point it, it's not showing as much as I would expect, but there's basically a ship that would throw like waves of sound waves, let's say like that, just to compare with what bats would use, like an ultrasound way of seeing things. So there are pressure waves that are propelled down, and then they reflect in the surface of the ocean or the subsurface of the ocean. And the way they reflect, we'll see a little bit more about this later, this can be used to infer the kind of materials that are in the subsurface, and then, of course, finding, hopefully, reservoirs of oil and gas. And the thing is, to explore this kind of reservoirs is not only one drilling attempt, but several of them, because you have to find the reservoir, but then map all the extent of the reservoir. So if we are able to reduce the error in these approaches, it would be a great advancement overall. So we looked up for solutions that already existed for this. The classical solutions had some limitations on it because the conversions seemed to happen a little fast or subdue to local minima. Since we're approaching this kind of problem, it's a very specific problem for geophysicists and who works on this. So since we're approaching from a computer science side of things, we had to get a lot of context on how to work with the data and interpret it. And existing quantum or quantum-based solutions had some limitations. Some of them used annealing that had a good result compared to what already existed in the literature. But other approach that caught our eyes was based on genetic algorithms. And this existing solution on the genetic algorithm had other limitations of needing too much qubits to represent the data, and also being prone, or because of the way they explored the solution space, they couldn't retain information at each generation when they were exploring. I'll get more a bit about that later. So we found a new way of doing this, where we unify the units that we're approaching in this genetic algorithm. In the genetic algorithm approach, And I will explain this using this infograph. We'll stay here for a while. First of all, a genetic algorithm, we can see this line at the bottom there. It's based on the biological, it's inspired by biology. So it's based on the theory of natural selection. So we represent data using bits in a classical genetic algorithm. Each individual of a population represents a possible solution for the problem. And at each iteration that we call the generations, we select which individuals were best to fit and solve the problem, to match the fitness function that we have. And the way these individuals approach or explore the solution space is through some operators, some genetic operators like mutation and crossover. During the mutation, each individual has a chance to have a gene mutated through a probability of mutation. So a bit could be flipped during the mutation. And in the crossover, the existing population would breed with the mutated population to create an offspring that we call the trial population. So at the end of each generation, we would select which, between trial and the existing population, which was the best to solve that. But that's the classical way of doing genetic algorithms. Our approach here, we combine not only the classical bits for representing these individuals, but also they coexist with quantum individuals. So we have both qubits representing data, representing information for some individuals, and bits representing for others. And we have them coexisting, so the classical individuals can contribute on the information and how the quantum individuals will explore the solution space. So when we initialize the quantum individuals, they emerge with information from the previous classical individuals. So the rotation we apply to the qubits at the beginning, they're already influenced by the previous classical generation, bringing up some genotypes, some information from previous best solutions. Then the mutation occurs. And in the mutation, the classical individuals also, or the classical population also influences how the quantum individuals are mutated. So there's a chance of a qubit being flipped, or actually not flipped, but being influenced by a gate if, and how, depending on how the classical algorithm performs. So let's say, for example, if an individual had a good result in the past generation, we apply only a Hadamard gate to do the mutation on the qubit in the quantum individual. If it had a bad solution, if it wasn't a good individual in the past generation, we apply an X gate. So this is the kind of decisions that we make, and the way we bring the classical information from previous generations to the mutation as well. At the end of these rotations, we measure, of course, the qubits to go forward. I would just keep calling the quantum generations as quantum, although they're classical here, but just for sake of understanding. So the measured quantum population now influences back the mutation of the classical algorithm, of the classical populations. The way we do that is to combine the best results from the quantum with the best results from the mutation that we have, and the classical individuals that we already had of course, they're controlled as well for a mutation rate. So there's a probability of combining bits from these three populations to generate a mutated population. With this mutation mutated, we do a crossover, as we would do in a classical GA. And then finally, we have this natural selection, choosing the best individuals from each one. So as I said, we would spend some time here, but it's important because from this, we get that the existing quantum solution would go through the part in the top only, and the classical would go in the bottom. We're mixing them up here. And from that, we have half the number of qubits that would be required for a quantum genetic algorithm. The existing literature approaches require the double amount of qubits. We're reducing that by half because we have them coexisting. And we have the classical individuals contribute to bringing the history, bringing the best solutions to the next generation, functioning as a memory that would influence how the next generation of quantum individuals will perform. And just to get a quick overview on what we are solving here, in the far left, we have a column that would represent the reservoir and how the acoustic impedance of the underground soil would be modeled. We don't know, but it exists. Then we emit a wave that we know, that wave we try to emit using the propagators that I shown in the previous slide. Then we measure it. So when we measure the results, we're trying to extract the waves we emitted and get a model of the reservoir underwater, underground. So this is done through a very complex equation called Zoprit's equation, and it's a nonlinear system that we have to solve. And basically to show some data that we can compare here, we have that incident P wave is how the wave that we're sending, they hit the underground, the soil with an angle of θ1, and it gets reflected. It gets reflected in an S wave, a secondary wave. It also gets transmitted. It gets transmitted in a secondary wave. What I wanted you to get from the slides that there is a lot of variables that we're trying to approximate here. And we compared our results, that's the dual unit, with the existing quantum approach, the hybrid, called hybrid, and the classical GA, to check how well would we approximate the three most important variables that we have in this kind of modeling. There's the velocity of the first wave, the velocity of the second wave, and the density of the first area. So the dual unit got the best results. I mean, it was close to the existing quantum approach, but here's please read as mean absolute error, but we have very close results, but it's a mean absolute error. But this incidence is measured over all angles. So we should go further in this analysis because every improvement in one approximation like this could mean a lot of better results. When compared how each of these approaches got to fit the fitness function, they got to match the fitness function. Here we have a chart that shows the mean fitness level. In the y-axis, we have it on log scale. So at each generation, we see that the dual unit got to improve the fitness over time, while the existing quantum approach had a higher fitness level, and the classical kind of stayed in the same in 150 generations. Of course, this could be extended for more generations. We interrupted into 100 generations here. But I wanted to show you this because it's not only about the mean error, but also how did this solution perform over each angle? Because if we took like the results for the angles from 20 to 40, we see that a lot of the results of the approximations from the dual unit reached zero error approximation. So we were the best results if we got that range of results. I always lose here, but you see from 20 to 40. But if we got from 40 to 60, maybe the hybrid and the dual unit would be similar. So what this tells us is that the dual unit actually approximates better the fitness function that we're trying to replicate. And the way we'd like to interpret this is that if we approach the GA, the classical GA, it has a good capability of looking at a solution and finding a good value to go deeper. The hybrid QGA, the existing approach for quantum genetic algorithms, it's good to explore the solution space. And the dual unit QGA actually brings together the best of both worlds, where we can find better solutions, but also explore the solution space. We performed a benchmark between the hybrid QGA and the dual unit QGA using Latin hypercube sampling for 500 parameters, ran it 30 times each. And we got these results of best fitness for each of them. We had other results, but these are the ones that are documented for it. And I wanted to highlight also this chart on the right, where we see that the distribution of the fitness for the dual unit was closer to a better value in all of the executions, while the HQGA got a more spread out result. So we believe it shows how it can fit better over time. Also, although it's a genetic algorithm, I joke here that it's evolving by itself as well, because we're exploring other applications. It's an optimization algorithm, so we can explore other fitness functions. So we've been applying this for multi-pit mining exploration, for crop rotation, and I would be happy to have a conversation with any of you who has interest in exploring this in other industries as well. Finally, I would like to say that we can embrace challenges today with new kind of solutions so we can unlock the future of quantum. And thank you for your attention. I'm open for questions.
Thank you so much. Okay, questions, please. Okay.
Yeah, there are a number of different quantum technologies out there. Which one were you using?
You mean, thank you for your question. Hardware-wise?
Yeah.
We ran this on Rigetti, but the thing is, I'll use your question to say another thing. The modeling of the individuals there require a lot of qubits if we want to model it, all the data. I mean, we used like the amount of qubits required can scale depending on how we are modeling it in the solution there. So when we use Rigetti, we use with the 80 qubit that was available a while ago. And so we couldn't, in this examples here, we ran on simulators for 200 qubits. We would require 200 qubits. And in the real quantum computer, we ran with 50 something. I can't remember right now, but I can get you back. I can get back to you.
Thank you very much.
No problem.